Good evening. Today we will talk about another application of the double integral, namely the computation of the center of mass of a piece of the material which can be represented by a plate of negligible thickness. So I usually go over this section because there is an equivalent of this for a more general object in 3 dimensions, but the formula follows the similar kind of framework, except it involves the triple integral, which will be taught later. I usually don't go over that particular section because the formula is very similar. So before we get into the topic, so to speak, let's actually go over a brief Calculus 1 review or Calculus 1 recollection related to this topic. And this portion, you probably don't need to actually write down anything about it. So actually, even before Calculus 1, let's say, even before Calculus 1, there was this concept of a center of mass for an object where the mass is localized at various points. So let's say, for example, you have some sort of an object in which the entire mass is concentrated at various points. This is, of course, a completely idealized representation, right? I mean, it's like, for example, you have, let's use actually 2 points so that we don't waste too much time with this, right? And to make it even easier, let's say you have 2 points in the plane, right? So let's say you have an object like a straight bar, but the length, the material that connects the two ends of this bar, that bar is basically negligible in terms of the mass. So the entire mass, let's say, is concentrated at the point x1 and y1, and the entire mass, and then, also the point x2, y2. So these points, I have mass 1 and then mass 2 at the point x2, y2. So in other words, the total mass of the object will be m1 plus m2. Okay, so the question is, how do you place the center of mass? Like, where is the point of balance for this entire system? And the center of mass, remember, I don't know if you remember because the notation differs from book to book, but the center of mass is denoted usually by x bar and y bar. And the formulas for the coordinates of the center of mass are the ratio between what we call the moments with respect to the y and the x-axis. So big M is the total mass of the system, if you want. The my is the moment. I'll explain what that means in a moment. No pun intended, right? In a second. So my is the moment with respect to the y-axis, and mx is the moment with respect to the x-axis. And the formula for the center of mass is my over mx for x over total mass, and then y bar is mx over m. So the idea is that if you go back to the picture here, let's just draw it with a different color here. If you want to balance the object, like in other words, if you want to figure out where on the horizontal line is going to be that coordinate x bar of the center of mass, that means you want to balance the object with respect to the y-axis. So in other words, how far or how close should you be to the y-axis so that the object is in balance with respect to the position on the x-axis. So that's why you have this basically relationship. The x bar, the x coordinate of the center of mass, is the moment with respect to y over the total mass, and the y bar is the moment with respect to x over the total mass. And again, in the discrete case, the moment with respect to y is simply m1 x1 plus m2 x2 over m1 plus m2, right, the total mass, and then y bar is m1 y1 plus m2 y2, same idea, right, the balancing with respect to the x-axis over the total mass m1 plus m2, right? So it involves the distances of the y coordinates to indicate, to compute how far it should be with respect to the x-axis. This is a discrete case, which of course is not that realistic, because obviously in practice the mass is not localized at finitely many points. Now we had a version of this in Calculus 1 when we said, well, what if the object in question, for example, is described by, there are variations of this, but let's say it's described by some function, or the portion between the graph of a function f of x. Let's go back to the original color here. So what kind of object is this, right, represented by this? This will be basically what we called a thin plate. In other words, it's a piece of the material of negligible thickness. Furthermore, instead of having the mass concentrated at various points, the mass is distributed throughout the plate. So basically the mass is going to be actually a function of x on its own. Now remember that there is a relationship between the density, the mass, and the volume. The density is mass divided by the volume, which means you could also say that the mass is equal to the product between the density in general and the volume. For a because in general the density is given by unit of mass per units of volume. Like for example, the density could be kilograms per cubic meters. On the other hand, if the object has negligible thickness, it could be more convenient to define the density in in units of area per in units of mass per units of area. So for example, you could have the density in kilograms per square meters. Again, when the thickness is negligible for this object. So in Calculus 1, we generalize somehow the problem from a discrete set of points by stating that maybe the density of the object is a function of x. The density, by the way, is denoted by rho, by the Greek letter rho, in most of these books. So this allows me, or this allows us in Calculus 1 to actually compute these quantities in terms of integrals, because this type of formula that we see here on the top of the page is replaced now by a Riemann sum. In other words, you're going to split the plate into small equal pieces, which correspond to a partition over the domain, and then you're going to basically approximate the mass for each thin slice of that partition with the mass localized at the middle of that slice. And then you kind of replace, of course, the summation here for the total mass and for the moments with a Riemann integral when you take the limit, of course, of that summation. So, for example, in the case of the total mass, the total mass of the plate will become the integral from A to B of the density times the volume of the the area, right? In the so the integral of the density times the times dx will be the total mass. And there is another formula that again it's going to give you the moments with respect to x and y, which I won't get into that again from Calculus 1, because now we're going to move on to the not rho of x, sorry, rho of x, right? So the function of x dx in Calculus 1. We're going to have two variables in Calculus 2 in Calculus 3 because we generalize this even further for the situation in which the density actually depends depends on both coordinates x and y. So with this background, so to speak, let's get back to our section here. So the object in question that we're going to talk about today, again, is going to be a thin plate, negligible thickness, but we generalize it, and by saying that the density, again given by units of mass over units of the area, now can depend on the coordinates at the point on the plate. So not just on x, for example, like in the previous case. So now it's just more general, right? So the density depends on the position or the point you pick on that thin plate, two-dimensional plate. So the domain of integration is represented by this plate. Let me state it here, right? So the domain of the resulting integral is the shape of this plate for which you want to compute the center of mass. So now the partition is going to be basically like a partition for a double integral, right? So if you imagine the plate being like this, generally speaking, and you do the partition, right, somewhere in the middle, right, after you take the limit of the Riemann sum, right, the partition for the double integral, you basically have a piece of the plate of dimensions of area dA, right? So that's the area of a small patch in the partition of D. If you use Cartesian coordinates, remember that's dx dy. If you use polar coordinates, remember that's r dr d theta, and so on. So what is the total mass? Well, just like before, the total mass of the plate is going to be now a double integral, because you have a summation by x and y, so a double Riemann sum, which gives you, of course, a double integral in the limit. So a double integral of this domain of the density rho of xy dA, and for the moment with respect to y, which will give me, of course, the position of the x-coordinate of the center of mass, analogously to calculus 1, that's going to be the double integral of x times the density dA, right? So the meaning of this product, by the way, rho times dA, it's the density times the area, which gives you the mass, right? So just to be clear, right? So when you multiply the density times the area, that gives me the mass. So for the center, for the moment with respect to y, you do the density, you do the mass times x, right? So how far from the y-axis should you be, right? The mass times the x-coordinate of that patch. And this is the moment with respect to y, right? And then the moment with respect to x, that's going to be the double integral of y now times the density dA. And so therefore the center of mass, x bar, y bar, is going to be my over m, mx over m. Sometimes people get confused with x bar being related to my over m, but again, remember, that's just the distance to the y-axis. It might be actually even easier to just put the integrals directly in the formula, which I'm going to do on the next page before we go over a couple of examples. So stay tuned for the next page. All right, so this is the formula for the center of mass. Just a small correction, and I'm going to write it in the comments. I just realized after I switched the pages. In calculus 1, the density was a constant. What you integrated was the function which was representing the plate, basically. So not the density. So that the density was a constant. Now in calculus 3, we have the density being dependent on x and y. And then, like I said on the previous page, the density times dA is basically the mass of that small portion on the partition after you take the Riemann, the limit of the Riemann sum. Okay, so let's find the center of mass of a plate given by the following equations, the following boundaries are bounded by y equals 1 minus x, y equals 1 minus x squared, y equals 0, and that's it. And then the density of this plate, let's say it's rho of xy equals ky. This k is a constant, and typically it's a physical constant, which has to do with the nature of the material, basically. So this tells me that the density is proportional to y only. Again, it can depend on both x and y. And so it's important also to, when you go over these integrals, to notice if there is any symmetry that you can actually infer. We'll talk about that in a moment. Because it may save you some time by not needing to actually compute all these integrals. But let's save that for later, and then we'll talk about this remark about possible symmetries. One of the confusing part actually about symmetries here is that it's not sufficient for the plate to be symmetric. The mass has to be evenly distributed to actually make some conclusion about the localization of the center of mass. So first of all, 1 minus x squared is an inverted parabola, right? So if we were to sketch this plate, so this is going to be also my domain of integration. It's like that. And the intercepts of this parabola with the y-x-axis are minus 1 and 1. The vertex is at 1 as well. And again, let's just thicken a little bit the margins here so I can visualize clearly the actual plate here. So in general, you need to compute 3 integrals to find the center of mass. So let's actually try to do all of them at the same time, because they should be too complicated. So the x-coordinate of the center of mass, in fact, let's actually save that for last because I want to make that remark. So let's do y bar first. So the y-coordinate of the center of mass, that's going to be the double integral of y times the density, which is k times y dA, and divided by the total mass, which is the double integral of k times y times dA. So k cancels. I mean, it will have a meaning in some sort of an answer if you have to provide the total mass separately or the moment with respect to x or y. K being a constant, you can just pull it out of the integral and cancel it with the one below. Let's see how we can compute the double integral. We can view this as Fubini theorem as a domain of type 1, meaning that I'm going to pick the outermost integral to depend on x, right? So there's your vertical slice. So the outermost integral is from minus 1 to 1. And pay attention here, for a given x, the bounds for y are whatever whatever y is equal to in terms of x. And it's already given as such, right? So y equals 0, y equals 1 minus x squared are the inner bounds. We cancel k before, so then I have to integrate y squared dA and then everything dx at the end. And divided, same bounds on the bottom, it's the same domain, except on the bottom we just integrate k times y. Since we canceled k before, that's just y dy dx. Alright, moving along, the antiderivative is y third over 3 with y between 0 and 1 minus x squared. And on the bottom is y squared over 2 between 0 and 1 minus x squared for y dx. Let's see, we have 1/3 1 minus x squared to the power 3 chosen a smaller power. I think I'm going to just give you the answer on the top because it'll take too much time to do it in details here. And on the bottom is the integral from -1 to 1, 1/2 1 minus x squared to the power 2. Okay, so dx. Okay, let's do this with a computer algebra system. Just enter this integral in Wolfram alpha or something similar, because this is kind of computationally heavy. I don't want to do it in details right now. So on the top, you're going to end up with 32 over 105. And on the bottom, you end up with 8 over 15. Okay, so let's actually check the bottom one just for completion here. I mean, just for the sake of it. So, because I don't want to raise this to the power 3 on the top, but let's do the bottom one. So if you raise that to the power 2, that's just 1 minus 2x squared plus x fourth. And then the integral of that will be x. Let's see this. So the integral will be x minus 2x third over 3 plus x fifth over 5 between -1 and 1. So we're going to have 1/2, 1 minus 2/3 plus 1/5. And then subtract 1/2 and plug in -1 now. -1 plus 2/3 minus 1/5. Obviously, if you factor 1/2, the common denominator is 15. And then you're going to end up with 15 minus 2 times 5, which is 10. You can pause me and then, go slower if you want to check this. Minus 10 plus 3. And then we're going to have minus -1, which is 15 again. And then minus 2 over 3, 2 times 5, that's 10. And then plus 3. Let's see what we get. 30 minus 20, that makes it 10. 10 plus 6, 16. Can cancel by 2, and that's 8 over 50. Okay, so going all the way back to the y bar, like I said, just take my for granted that the top is 32 over 105. And if we simplify this a little bit further, it simplifies by 4, this by 5, and you're left with 21. No, this is 3 on the top, right? Because you simplify by 5. So 4 times 3 over 21, actually you can simplify it further here, because you can simplify by 3, and so this is 4 over 7. Obviously it should be between 0 and 1, right? Going all the way back to the shape of the plate, it's somewhere between 0 and 1, the center of mass. Okay, but here's the thing. What about x bar? And I'm going to do that actually a little much faster, because we can notice something important here. First of all, notice that the denominator, we already did it, it's 8 over 15, or I should say, so again, 8 over 15 after you cancel the k, that constant. But the top is going to be the double integral of x times k of xy, k of y, ky, dA. Right, the moment with respect to the y-axis. So again, the bounds will be the same from -1 to 1 and from 0 to 1 minus x squared, kxy dy dx over 8 over 15. The innermost integral, here I can pull the kx out because it's a constant. And the antiderivative is y squared over 2. And when you plug in the bounds, that's 1 over 2 1 minus x squared squared dx 8 over 15. Okay, so you may remember from calculus 1 that if you integrate an odd function over a symmetric domain, the integral is 0. Symmetric domain with respect to a symmetric domain with respect to the origin, basically, right? So from minus 1 to 1. Why is that? Because, again, don't write this down, but if you look at a typical odd function, right, if you plug in minus x, you're going to get the negative of the previous function. So if the domain is symmetric, you have a portion on the positive region and the same area under the negative region. So the integral, these two portions will cancel out when you do the integral, again, over a symmetric domain. If you look carefully of this expression here, kx times 1 minus x squared quantity squared, if you plug in minus x, you just have an extra minus. That's the only difference. So the integral here is 0 because the function is odd over a symmetric domain. But I claim that even before you actually set up this integral, you could have noticed, and this is the important remark to make here, you could have noticed that x bar is 0 because there is some symmetry in the plate, first of all, and some sort of even or symmetric distribution of the mass. So if you go back to the plate here, because the mass only depends on y, on the y coordinate, it doesn't depend on x, right? So I mean, it doesn't matter whether you are left or right, okay? The mass is evenly distributed with respect to x. The only difference in mass is due to the y coordinate, not on the x coordinate. So that's the reason why you know from the beginning that the center of mass ought to be on the y-axis. And then obviously the question is, what is that y-coordinate of the center of mass, which we just did it before. In my next example, I'll show you another case in which you have another type of symmetry that kind of, again, saves you from the pain of computing one of these integrals. So stay tuned for the next page. Okay, so in this case, let's say the plate is given by the portion of the circle in the first quadrant, the circle given by x squared plus y squared equals 1. Let's say that to have the bounds kind of nice, right? So the plate in the form of a quarter of a disk, if you want. And then the density, let's say it's some constant square root of x squared plus y squared. All right, so let's notice from the beginning that there is some important symmetry here. Notice that if I interchange y with x, I get the same thing, right? So if it's y squared plus x squared is the same thing, which means the density or the mass, if you want, is evenly distributed with respect to the y equals x. That means I know for a fact that the center of mass is located on the line y equals x. Or in other words, I know for a fact that the x and the y coordinate of the center of mass are the same. Okay, so then again, I can save computing one of those three integrals that come part of the formula for x bar and y bar. In this case, it won't matter which one you're going to pick, so let's just do the first one, right? So x bar, once again, is the double integral of x times the density over the double integral of the density itself, the total mass. Okay, how do we solve it? Well, the density is square root of, let's put the k out, that'll cancel again. Given by the expression here, I mean, that gives me the density. That x squared plus y squared looks promising. And of course, primarily the shape of the domain, polar coordinates are the way to go when we compute the this double integral. So look at the formula for the double integral in polar coordinates. And the domain, by the way, in polar coordinates, obviously now for the radius is between 0 and 1. and for the polar radius is between 0 and pi over 2. Okay, moving along. In polar coordinates, we're going to have bounds for theta on the outside, and followed by the bounds for r on the inside. And then on the top, we have r cosine of theta corresponding to x. And remember, x squared plus y squared is r squared. The square root of that is just another r. That's the square root. dA becomes again r dr d theta. And on the bottom, we just have r from the radical, and then r dr d theta from dA. Both integrals split into a product of two integrals, the integral in theta times the integral in r. So on the top, I'll have r third. On the bottom, the integral in theta is just 1 d theta, and the integral in r is of r squared dr. Okay, these are not too bad to compute. So the integral of cosine is sine between 0 and pi over 2. Here is r fourth over 4 between 0 and 1. Theta 0 pi over 2 and r third over 3 between 0 and 1. Alright, so sine of pi over 2 is 1 minus 0, and then 1/4 minus 0. On the bottom, pi over 2 minus 0, and 1/3 minus 0. So 1 over 4 divided by pi over 6. That's 6 pi, that's 6 over 4 pi, which simplifies to 3 over 2 pi. Which, by the way, it's approximately 0.48 as expected. It should be somewhere in between 0 and 1 along that radius. Okay, so as you notice up until this point, see, these sections can go a little bit faster because the main tool is a double integral, which we already talked about how to compute it. So all is new is just basically a new formula that involves double integral. So the next section is the same, yet another double integral which serves a different purpose. How you compute the double integral, it all depends on the shape of the domain and the function to integrate, whether you decide to be in polar coordinates or as a type 1 or type 2 in Cartesian coordinates. So that's it for today, and I'll see you next time.